Hello, my name is Martin Kacer.
I'm working as a security researcher for Mobilium, and during this talk I would like to cover 5G mobile networks and the interconnect threats. First, allow me to introduce the company. So, Mobilium is a global company with global footprint, mainly providing the roaming and network solutions, fraud and risk, testing, monitoring, mainly for the mobile operators and the carriers, but also security solutions like signaling firewalls, threat intelligence, and other products. I'm security consultant working for Mobilium. In the past, I developed open source signaling firewall, did some Wireshark contributions, and also contributed to the GSMA security guidelines for mobile operators, covering SS7 diameter GTP-C and 5G protocols, and also did some Android development. Now, during this talk, let's focus on the interconnects. So basically, interconnects is something like private networks between the mobile network operators. Mainly, they are used to allow the roaming while the subscriber is moving between one country and another. And these are private networks compared to the internet, for example. And 5G introduced new architecture and basically new core networks also. So let's cover this. So basically there exists two models how the 5G could be deployed. One is called non-standalone architecture. Basically this means that the 5G RAN will be deployed, but the core network will remain the same. So this will be basically the evolved packet core 4G network, just the RAN will be 5G. In this scenario, the interconnection between mobile operators will remain the same, diameter GTP-C and GTP-U. The second model is 5G standalone architecture, which means that there will be 5G RAN, but in the same time also 5G core network. And now if there would be interconnections between operators, there will be 5G interconnects using protocols like HTTP2 and GTP-U. Here is just the overview, how it looks like. So behind the 5G new RAN, we can have 4G or 5G core network. In this talk, let's focus on the 5G standalone architecture, because from the security perspective, if there is 4G core, we need to apply the similar security like for the diameter security and GTP-C security. Here is the evolution. So from 4G to 5G, there were several changes. So for the authentication and mobility management, in the past in 2G, 3G, mainly the SS7 protocol and with the MAP has been used. In 4G, this was replaced by the diameter. And in 5G, we will use HTTP2 to deliver basically the subscriber profile, authenticate the subscriber, and other messages. For the session management in 2G, 3G, and even 4G, the GTP-C protocol has been used to establish the sessions. In 5G, also the HTTP2 will be used to replace the GTP-C. For the user plane encapsulation, so basically where the IP packets are encapsulated between the core networks, basically always the same is used, GTP-U. Regarding the network elements evolution, so basically these are the systems which are inside the core network. In the 2G, 3G, and 4G, we use the name like network element. In the 5G, because it will be service-based architecture, name network function is used. So we see that the network element names are now changed. In 5G. We will have UDM. So this is the main subscriber database storing the subscriptions of the users. MSC VLR in 4G and 5G, this network element is not there simply because the voice is not natively supported by the core. But IMS, IP Multimedia Subsystem, deliver the voice service. So the 4G and 5G is something similar like providing the IP bearer for the subscribers. SGSN or MME SGW has now evolved into AMF, SMF, UPF, so access mobility management function, session management function, and the user plane function. The GGSN or PGW in 4G is now in 5G, SMF, UPF. 5G regarding roaming and interconnects introduced significant improvement regarding the security. So now all the interconnections should be protected by N32 interface. This interface should be interface between the MNO to MNO, basically mobile network operator to other mobile network operator, and providing mainly the authenticity, so to prevent some message spoofing, integrity, that the messages has been not changed by some party in the middle, and also confidentiality, full confidentiality, or at least to protect certain fields inside the signalization. Here, on the network edge should be deployed SEP, basically, which is Security Edge Protection Proxy, and these network functions should basically terminate or establish the N32 interconnect. Regarding the N32, so it is divided into two separate, let's say, sub-interfaces. N32C, which is really direct SEP to SEP over TLS. This is basically kind of handshake and to negotiate on the security capabilities. And second is N32F. This one is to deliver actually the signaling messages after the handshake. So it can be protected by using TLS. This is something if there is really direct link from one operator to other, then we can rely on the transport security. And the second is kind of application layer security. This is basically PRINCE, protocol for N32 interconnect security. This was designed to allow also some parties in the middle, like roaming hub or some HTTP proxy, which can forward the N32 message, but basically still the mobile operators could secure somehow the messages with some signatures or integrity or even confidentiality of certain fields. Regarding all this, so keys should be exchanged between mobile operators, and this is covered by the 5G key management procedure. So it is public document GSMA FASG 34, defining how the operators could exchange basically the keys to enable this 5G roaming. Current stage is manual, but in the future it is expected to automate the process. Here is just the overview. So it can be seen on this picture that N32C should be direct links between the operators, while N32F could be direct, or even could be go through, for example, some intermediate proxy from MNO2 over, for example, roaming hub towards the MNO4, and the similar even if there are two hops in the middle. In this way, still some MNO to MNO security could be provided, even if there are intermediate hops. Without this protocol, basically it will be more like hop by hop security, and the originating and terminating MNO could not really verify the messages or protect even by encryption certain fields. Still, even if this has been introduced in 5G, which is significant improvement, still there are possible attack vectors, and basically in this picture or diagram it is seen that if the MNO3 interconnects some third party and this third party sends some illegal message, still the message can be tunneled through the secure interconnection towards the MNO4 network. In this way, for example, the message can target MNO4 subscribers or possibly inbound roamers in MNO4 network, for example, which are not belonging to MNO3. So there is no reason why these kind of messages should be allowed towards the MNO4. This means basically that still there is need for application layer firewalling inside the protocol or inside the communication, and there is still need for some signaling firewall inside or after decrypting the N32. Regarding this, there exists document GSMA FASG, which performs some risk assessment and classification of the 5G messages. And additionally, for 5G messages, you can also refer to this public repository, and it includes basically Open API or the scheme defining the messages, which is very useful. 5G messages and interconnect filtering. So basically, the messages could be classified based on the way how they should be used. There exist also intra-PLMN messages only. This means that some messages should not be used between the operators and should really stay just within the same network. They are within the GSMA, they are classified as category 1, and these messages could be dropped when received from the interconnect. Then there are messages which need to be allowed, basically because we have the roaming between the networks. There could be communication from VPLMN, visited network, to home network, or in opposite way. These could be classified or are classified within the GSMA as category 2 and category 3. Additionally, in 5G, there could be also other messages like network-to-network communication, even if there is not involved subscriber. And, for example, also therefore, in later releases, there could be SMS service, and this is more like A party to B party communication. So it is a bit different than the roaming situation, and also other messages. Regarding your testing, or if you're interested in testing 5G and set up some lab environment, you can use these projects. So one is free 5G Core. So it is open source project. Second is GNB Sim, basically 5G run simulator. This is useful that if you are not willing to use real physical SIM card with some card reader, how you can attach basically or simulate the attach of the UE, which can be useful if you are willing then later on to test, for example, some HTTP2 messages towards the core. Regarding the client for testing, so basically you can use or you can try to use open API generators to generate the client and the server for you. Other way is really just to write your HTTP to client directly for the testing, basically without the generators. Regarding the limitations, so free 5G Core, currently there is no SEP or no OAuth authentication of the NRF. Regarding the setup, so you can do something similar. For example, install Ubuntu VM, inside deploy free 5G Core, and install GNB Sim. Then from the host or even directly from the Ubuntu VM, you can use your HTTP2 client to inject the messages and send it and test it towards the core. So on the left panel, you see just the examples how to, or of the running of the wall. Regarding the open API generators, so if you are familiar with previous generations and protocols like SS7, there was used ASN1, like abstract syntax notation, which was basically some kind of scheme. And based on this, you were able, by using ASN1 compilers, to generate the encoder or decoder for the payload. Something similar is used for the HTTP2 and Open API. So basically, these define or prescribes the messages, how they should look like, how the API should look like. And after, you can compile your code, which will create some skeleton of the client and the server. But alternative is also you can write your custom client. Why? Mainly because HTTP2 and JSON messages are really easy to encode, and there is no significant hex or byte encoding like in SS7 there was BER, or some TLV encoding in the diameter. Here is simple example of HTTP2 Python client. So it is really easy. You can open the connection towards the target IP address and port using the HTTP2, and then just send the GET request, for example, for target URL, and something similar for POST. So you will just define the target IP, port, POST, URL, and then the payload. So basically inside is the JSON. Additionally, you can specify, for example, the message headers. And then you read just the response back. Now, let's imagine that the free 5G core is some real target network, and we can imagine that by using our client, we will try to inject some messages towards the target PLMN. So we can start maybe with one example. This is RegisterNF Instances. The client or the producers of these messages should be basically network functions or SCP or NRF, and consumer is the NRF. NRF is some network element which acts as some registrar function that every network function should register towards the NRF, and NRF also provide the information what network functions are registered there. So it works basically in both ways. There is also a possibility that the one PLMN to other communicates. There is NRF to NRF interface, and basically it can query also what are the target network elements. So you can see that we can craft easily message HTTP GET towards the target URL, and there we have we are acting like AMF and querying the NRF and asking please provide us the UDMs in the PLMN network. Now, here is just the overview how it can look like. So we can receive this message from one MNO1 towards the MNO2 and reaching the NRF. Here, basically the impact will be topology discovery and how the response looks like. So this is just capture from the Wireshark that after sending our GET request, we receive 200 OK and the payload back. And we can see now we have also all the details like IP address, NF instance ID, and even service name. So all the APIs which are supported by the target network function. So this can be useful to perform some network discovery, topology discovery of the target network. Other example of additional message is the RegisterNF Instance. So here, this message it is produced by network function or SCP towards the NRF. Now the difference is that the register or registration should be done within the intra-PLMN only. So for example, if such message is received through the interconnect, it should be blocked to prevent some not wished behavior in the network. Here we can see how it is easy to grab the message. So just sending the delete regarding or towards the target URL, and here should be some NF instance ID. This we can retrieve through the search as seen on the previous slides. Here is just the global picture, like one network can send it towards the other network, send the register target NF, and possibly can maybe disrupt the service that the NRF will be not able or will be not consider the target network function as registered anymore. Other example of next message is get free GPP registration. Now the producer is network exposure function, consumer or the targeted system is UDM. There is not much description in current free GPP releases, but it is intra-PLMN message only, so it should be not normally allowed from the interconnect. Example is quite simple. We can send the HTTP GET towards the target URL. Then there is the IMSI, and we are asking for the registration of AMF free GPP access. And here is the global picture, like one network can send this message towards the other network. Here we have our UDM. And by this message, basically, attacker can retrieve the subscriber route location, like what is the current AMF serving the subscriber. This can be some precondition for later attacks, so we will see it on the following slides. Here is the example of the FreeGPP registration, get FreeGPP registration response. So we can see that MCC, MNC are provided. Then we see the AMF instance ID. So all the information which can help us to identify really the exact AMF which is serving the given subscriber. Now provide location info. So here producer is the UDM, consumer is the AMF, and we have some FreeGPP description. Here the HPLMN communicates towards the VPLMN, and this is basically normal service that the GMLC should be allowed to geolocate the target subscriber. The illegal scenario is if the different network, then what is not the home network of the subscriber is trying to geolocate the target. Here is also the example request, so we can see that we just inject the post towards the target IMSI, and requesting all information what we can get. Now here is the global picture. Again, MNO1 send this message towards the MNO2, towards the AMF to retrieve the exact cell location. And now how the response looks like. So we can see there is quite everything. We can see there is MCC, MNC, and we have also cell ID and the UE location timestamp. So basically, cell ID can be later translated into exact geolocation like longitude, latitude of the subscriber, and we can really precisely track the subscriber. Why this is somehow risky? Mainly because what we see currently in SS7 or diameter in the existing networks, there are really active surveillance by some surveillance companies or state even agencies using this as a way to geolocate the phones, geolocate the subscribers actively. And this can be expected also to happen in the 5G. Regarding implementation specific vulnerabilities, so the above was mainly covering some generic cases according to specification if there is some lack of the filtering. Now, of course, depending on the implementation of the target 5G network, there could be also specific vulnerabilities like parameter injections, even SQL injections, JSON deserialization attacks, buffer overflows, OAuth issues, lack of maybe granular access control, access token abuses, and even others vulnerabilities which can be really implementation or even deployment specific. Here is just a free 5G core example of some injection of the parameter by crafting or using the following request. So basically sending the HTTP GET towards the UDM, we can inject the parameter PLMN ID, and as you see, it is not properly formed, so it is not some MCC, MNC there, but really message name, which is later on used by the UDM towards the UDR. Here is also trace. What is here? What can be seen? So we can see that by sending this message with the injection, after UDM sent towards UDR different message, which was not expected, like authentication data, authentication subscription, which is actually querying the AUC data. And then the UDR responds back with the AUC data. Fortunately, towards our HTTP client, the response from UDR was not forwarded. Why this is risky? Because normally the UDR should be not directly accessible and should be accessible only internally within the PLMN, not from the roaming. So this is kind of exposure and something new in 5G, that now even the AUC can be somehow reached through specified messages. And here is the flow, how it looks like. So basically the HTTP2 client was sending the message with the injection towards the UDM. UDM was not properly sanitizing the parameter, and just forwarded it towards the UDR. This means that the UDR interpreted as a different message and sent back the query authentication subscriber data response. Fortunately, the UDM did not forward the message to our client. Here I opened also GitHub issue for this to basically fix this. This is just an example of some vendor-specific vulnerabilities which can be really introduced by the implementation, and it can be really dependent on the target technology. Here is also example of other risky messages. So all these APIs it really depends what the target network will support. If it will be like release 15 compliant or release 16 or even more. And here is examples of some additional geolocation messages, or even there could be done the impersonation like ROGU. We can register basically ROGU AMF towards the UDM or ROGU SMF, and later on this can be abused. Then also there would be SMS messages, so we can see maybe some SMS spam or spoofing, and there are plenty of other messages. You can check the open APIs, so there are really plenty of messages and quite significant attack surface. And now regarding the conclusion, so basically in 5G, the significant improvement is that the interconnects are really confidentiality, integrity, and authenticity has been introduced on interconnects. The N32 and even N9 should be protected. However, regarding the signaling attacks, this still could be received inside the N32 tunnel, and therefore we need some application filtering. And in 5G still the security controls which would be needed are signaling firewall, signaling intrusion detection systems. Basically this could be separate system which continuously audit if the firewall or other filtering is efficient and if it is working properly. Threat intelligence to see the global picture, who are the sources of the illegal activity, or what really attacks are being exploited in the wild, and which are more maybe just theoretical one and which are really threat to the networks, and then some regular vulnerability scanning and security audits. So thank you very much for listening to this talk. Feel free also to contact us or contact directly me, and we can try to provide answers. Thank you very much.